In the previous portion of the lectures covering Newton's laws, I went through an example where all of the forces acting upon an object canceled out. If that happens, then the acceleration of the object is equal to 0. In that specific case, the object was at rest. Let's now see what happens with two basic examples for this video with what happens if there is an acceleration. If there is an acceleration, this then means that the forces acting upon the object do not cancel out. Let's go ahead and examine two situations where that is the case. In the first of these two situations, I'm going to use this particular example as a bridge, if you will, in the gap between kinematics, which we started in the previous unit, and now dynamics here in this unit. Recall in kinematics that it's concerned with the mathematical description of motion, but at no time during that unit did I say a word about what caused any of it. That's what we're going to do here. Okay, let's take a look at the first of the two examples for this lecture. Okay, a hockey puck with a mass of 0.1 kilograms slides across horizontal ice. The puck has an initial speed of 5 meters per second, and it comes to rest after 5 seconds. Now, just to visualize the problem, let me use the eraser here sliding across the desk to illustrate. The problem begins the instant that I let go of the eraser. The instant that I let go of the eraser, it has a speed to the right-hand side at 5 meters per second, and it ultimately comes to rest after 5 seconds. The situation merely looks like this. Once again, the problem begins after I let go of the eraser. Okay, now in part A and in B, we're supposed to do a little bit of kinematics like we would have done in the previous unit. Find the puck's acceleration and the distance traveled. All right, so let's take a look at the kinematics first. Okay, as we do, by the way, let's note immediately that the mass of the puck is 0.1 kilograms. We'll need that for the dynamics later on. Okay, and then here's what we're getting. Okay, we'll say that the puck starts horizontally at the origin, so the initial position x naught is equal to 0, and it initially is moving to the right-hand side with a speed of 5 meters per second. Okay, and then it ends up at rest over here with a final speed of 0. The time for this to occur is given to us as 5 seconds, and then there are two unknowns. We're going to have the displacement here, that's the final position x, as well as the acceleration. Okay, now in part A of the problem, it does ask to find the acceleration. And so if we go back to the previous unit, we're going to use the following kinematics equation to do so. V equals V naught plus AT. So recall this kinematics equation that describes velocity as a function of time. Let's go ahead and plug in the final velocity V as 0, like so. And now in this expression, the only unknown is the acceleration A, which we can solve for. So move the V naught here to the other side. We pick up a negative sign when we do, and then divide by the time t to get the acceleration by itself. Like so. So I then, therefore, end up with negative and then 5 meters per second divided by 5 seconds. This is just negative 1 meter per second squared. Now recall what the negative sign means. It means that the acceleration vector points to the left-hand side on the diagram. So let's go ahead and immediately note that here as the following vector, like so. Okay, next part B. Let's go ahead and calculate the distance traveled. In order to do so, we're going to use the other kinematics equation that we saw in the previous unit. Okay, so recall position as a function of time. That's this expression here. And now there's no algebra to perform here because we know what everything is on the right-hand side. The initial position is 0, and then plus 5 meters per second times 5 seconds, plus 1/2 times negative 1 meter per second squared, times then 5 squared. So let me just go ahead and plug in everything. All right, so 0 and then 5 times 5, plus 1/2 times negative 1 times 5 squared. And this then ends up being a final position x of 12.5 meters. So the object slides 12.5 meters in coming to rest. Back in the previous unit in kinematics, this is as far as we would have gone. But now we're going to go one step further. Now we're going to take a look at the dynamics. So let me go ahead and erase the board here. Okay, so now watch the situation with the eraser. After I let go of it, like so, how many forces are acting on the eraser as it slides to the right-hand side and comes to rest? There are 3 forces acting. Let's examine them. So now we're looking at the dynamics. So as the object slides to the right vertically, we have 2 forces. We have the weight, mg, pressing downwards, and then we have the normal force upwards, like so. Recall where the normal force comes from. It's a consequence of Newton's third law. So for example, in my demonstration, the eraser presses down on the desk. That's the action. And then therefore the reaction is that the desk pushes back upwards. That's the normal force. The normal force, of course, also is applied to the hockey puck in the problem. Now there is no acceleration vertically. So because of that, then these two forces cancel each other out. The normal force is equal to the object's weight. But now, horizontally, after I let go of the eraser, we have the force of friction acting upon the eraser. The force of friction is what causes the eraser, of course, to slow down. The force of friction always opposes the motion, and we refer to the force of friction as small f. Now, just to clarify, after I let go of the eraser, there is no force acting on it to the right-hand side. So then, therefore, the force of friction causes the acceleration to the left-hand side like so, and now we're going to use F equals ma to add up the forces here in the horizontal direction. There's only one force acting horizontally, and that's the force of friction. So the force of friction is equal to the net force. It's equal to ma. And now at this point, we just plug in the numbers. When I plug in the numbers, by the way, I'm going to ignore the negative sign here for the acceleration, because recall that all that the negative sign tells us is that the acceleration vector is to the left-hand side. We now know what causes that, and that's the force of friction. So let's just go ahead and plug in the numbers here to calculate the magnitude of the force of friction. This is equal to the mass of 0.1 kilograms, and then multiplied by the acceleration of 1 meter per second squared. This ends up being then just simply 0.1 newtons, like so. So in this example, we're bridging the gap between what we did in the previous unit on kinematics, mathematically just describing motion, and now taking a look at the causes of motion. One last thing before we move on to the second example for this lecture, and that is the two n's that appear here in this problem. Just be careful about which n is which. This right here is the abbreviation for newtons, which is the unit. This right here refers to the normal force, okay? Okay, let me move my screen to the second example, and I also have to erase the board as I do. So let me erase first. Here's my eraser. Like so. And now let's take a look at the second example. And this second example involves an elevator. Let me read the problem to you. A person with a mass of 75 kilograms is standing on a bathroom scale while in an elevator. What does the bathroom scale read for each of the following situations? In part A, the elevator moves with constant velocity. In part B, the elevator accelerates upwards at 2 meters per second squared. In part C, the elevator accelerates downwards at 2 meters per second squared. In order to answer this problem, however, we have to first of all answer the following question. What force acting on a person does the bathroom scale actually directly read? Let's phrase that here on the board. So while standing on a bathroom scale, what force acting upon the person does the bathroom scale directly read? Let me illustrate. Okay, right here, I've got a rather beat up old bathroom scale. Let me go ahead and stand on it like so. And right now, there are two forces acting on me. There's my weight, the force of gravity downwards, and then there's the normal force upwards. Which of those two forces acting upon me does the scale directly read? It reads the normal force. And here's why that is. What the scale actually directly reads is the force of me pressing into it. It does so, by the way, by means of a spring. Think of that as the action. The reaction, however, from Newton's third law, is that the scale pushes back upwards on me. That's the normal force. That's what the bathroom scale reads. So then therefore, in this context, the bathroom scale is sometimes referred to as the apparent weight. Excuse me, the normal force is referred to as the apparent weight. Let me go ahead and write this down. Okay, so the scale directly reads the force pressing into it. By Newton's third law, N3L. By Newton's third law, that's the same as the scale pushing back upwards. That's the normal force. That's what the scale directly reads. Once again, in this context, the normal force is sometimes referred to as the apparent weight. So that's what we're asked to find in the problem, the apparent weight, the normal force in each of the three situations that are being depicted. Okay, pause if necessary and copy this down. I'm going to go ahead and erase now, and now let's take a look at parts A, B, and C. Okay, so let's note first of all that the mass of the person is 75 kilograms. And then we have part A of the problem. So here's a simple diagram. Here's our little person like so, standing on the bathroom scale, and the elevator in part A is moving at constant velocity. What this means is that the acceleration is equal to 0. Now, does it matter if the object is at rest, or if it's moving upwards at constant velocity, or downwards at constant velocity? It doesn't matter. There's no physical difference, if you recall, between an object at rest and an object moving in a straight line at a constant speed. Both of those situations are at a constant velocity. If the velocity is constant, as it is here in part A of the problem, this then means that the acceleration is 0, and then therefore the forces acting on the person cancel out. There are two forces acting. We have, first of all, the normal force upwards, and the force of gravity, the person's weight downwards like so. And because the acceleration is 0, it doesn't matter which way the object is moving as long as the acceleration is 0. This then means that these two forces cancel each other out. The normal force is equal to the object's weight. So yes, when you stand on a bathroom scale in the morning as you're getting ready for school, that's reading your weight. But it's reading your weight only because it's directly reading the normal force, which is equal to your weight, as long as your acceleration is equal to 0. Okay, let's go ahead and plug in the numbers here. So I have 75 kilograms for the person's mass, and then multiply by 9.8 meters per second squared, and this is 735 newtons. Don't be surprised by big numbers associated with forces in terms of newtons. The reason for that is because 1 pound is actually a lot larger than 1 newton. You don't need to notice off the top of your head, but the conversion factor between the two is that 1 pound is equal to 4.45 newtons. So just to give you some context here, this person who weighs 735 newtons, if I divide by 4.45 newtons per pound, that's the same thing as 165 pounds, just to give you some context. Okay, let me do a little bit of erasing here. Okay, now we're taking a look here at part B. Let's draw upon your experience here as we approach the problem. In this case, the elevator has an acceleration upwards of 2 meters per second squared. So presumably everybody here has already ridden an elevator before. You walk into the elevator, the doors close, and then it begins to accelerate upwards. Okay, what do you feel when that happens? Well, you feel yourself get pressed into the floor a little bit. So then therefore, if you were standing on a bathroom scale when this happened, would the scale read a value equal to, greater than, or less than your weight? Of course, it's going to read a value greater than your weight. Once again, that's the normal force. We're asked to calculate the apparent weight. Because we do have an acceleration here in part B of the problem, the two forces acting on the person, the normal force and the person's weight, do not cancel each other out. The normal force has to be larger than the person's weight because the acceleration is upwards. And then here's how we apply F equals ma in a situation such as this. By definition, always think of the direction of the acceleration vector as the positive direction. And then therefore any force vector that points in that direction is thought of as positive. Any force vector that points in the opposite direction is negative. And then here's how we add up these forces by using F equals ma. So we have the sum of the forces equals the net force, like so. Once again, the normal force pointing upwards in the same direction as A is thought of as positive. The person's weight in the opposite direction of A is thought of as negative. And now what we do is we solve for the normal force, we solve for the person's apparent weight. So let's go ahead and move the actual weight mg to the other side, like so. And now let's go ahead and plug in the numbers. As we do, notice that yes, you are going to experience an apparent weight that's greater than your actual weight by this amount. So we have here 735 newtons plus ma. So 735 plus then 75 times 2, and this works out to be 885 newtons, like so. So you feel yourself pressed into the floor a little bit when the elevator is accelerating upwards, therefore your apparent weight is greater than your actual weight. And now let's take a look at part C. Once again, we'll draw upon your own experience as we do. So in part C of the problem, in this case, what we're given is that the elevator is accelerating downwards at 2 meters per second squared. Once again, let's draw upon your own experience. You go into an elevator, the doors close, and then the elevator begins to accelerate downwards. As it does, what do you feel? Well, you feel yourself a little bit lighter. Therefore, if you were standing on a bathroom scale, it should read a value that is less than your actual weight. Let's see if it does. In this case, once again, the force of gravity downwards and the normal force upwards do not cancel out. But in this case, the force of gravity downwards has to be a larger number than the normal force upwards, like so. Incidentally, by the way, when I draw these force diagrams, of course, they're just sketches, but I am taking care to show that this force vector here, in this case, is bigger than this force vector because the acceleration is downwards. And then here's how we add up the forces. Now we think of the downwards direction as the positive direction. Therefore, any force vector that points in that direction is thought of as positive, and any force vector in the opposite direction is negative. So when I add up the forces by using F equals ma, we now have the following. Like so. So notice that mg now in the same direction as A is positive, and the normal force in the opposite direction is negative. And now we just algebraically solve for the normal force. So to do so algebraically, what I'm going to do is just switch these two terms, and when I do, this is what I end up with then for the normal force. Like so. Notice that the apparent weight, the normal force, is going to be less than the person's actual weight by this amount. And now we just plug in. So we have here 735 newtons, and then in this case, minus 75 times 2. And this ends up being 585 newtons, like so. So yes, your apparent weight is less when the elevator is accelerating downwards. Now to conclude this example, let's take a look at a couple of other scenarios here briefly for part C of the problem. Let me rewrite this expression, like so. Let's say in part C of the problem that the acceleration downwards was not 2 meters per second squared, but was instead g, 9.8 meters per second squared. What would happen in such a scenario? Can you picture yourself in the elevator as that happened? Well, from your point of view inside the elevator, you would just be floating around the elevator. If it was accelerating downwards at 9.8 meters per second squared, you would be in free fall as well as the elevator itself. So then therefore, what should your apparent weight equal in that situation? Watch what happens from this equation. So now what we'll do is we'll set the acceleration equal to g. If the acceleration is equal to g, notice that these two terms cancel out and the normal force is equal to 0. Your apparent weight is equal to 0. This is what is known as weightlessness. Weightlessness is when your apparent weight, the normal force, is equal to 0. And then lastly, let's see what happens in this same equation if the acceleration downwards is greater than 9.8 meters per second squared. Can you picture that? Where would you be inside the elevator if its acceleration downwards was greater than 9.8 meters per second squared? You would be up against the ceiling. Here's what that would look like, first of all, mathematically with our expression. So now what we'll do for this last scenario is we'll set the acceleration greater than g. So if the acceleration is greater than 9.8 meters per second squared, notice that this number is negative. So if the normal force is negative, does it still point in this direction? No, it now points in the opposite direction. Like so. So then therefore, yes, you would be up against the ceiling and the normal force would be pressing downwards like so. If you're having trouble picturing this, I can actually demonstrate it for you very easily in the following way. What I'm going to do is I'm going to take the eraser and we're going to think of that as the person inside the elevator, and then we'll use my hand here to depict the ceiling. What I'm going to do is I'm going to accelerate my hand downwards at a value greater than g. Watch what happens when this does, or when this occurs. Like so. Notice that the eraser was against my hand the whole time, therefore the normal force vector points downwards. Okay, I'll go ahead and conclude this portion of the lecture here.